Welcome back to the Rad Lab Podcast presented by Tennessee Tech's Chemistry Department. Lastly, we spoke about the Curies, and we're going to continue that conversation. What did we talk about last time, Dale?
We talked mainly about a little bit about their lives, and then talking about being brought together and meeting and basically finding like-minded dedication to science, and how this was a very unexpected but very nice account. We talked about how Marie, who initially didn't know how to boil soup, became a homemaker because of her intensity to make their life with Pierre something that was very nice. I think today we'll begin sort of with the birth of Irene. Their first child was in 1897, and this initially caused some stress on the household because there was only Pierre, who did not really have much interest in taking care of Irene. And so Marie had all of the responsibilities and still wanted to work in the lab, because that caused quite a bit of stress until Pierre's father moved in with them, and they were able to go to a little bit larger house, and he took care of Irene then.
And they weren't making a lot of money, right? Because he was like a entry, like lab tech kind of position at the university.
Exactly. He was at what they called an industrial university. It was for physics and chemistry, and he was what we would probably call a laboratory supervisor, and oversaw putting together the labs and what labs the students had to accomplish.
Yeah. And Marie was a grad student, so she wasn't making...
Well, she actually had a small grant to study the metallic properties of various metals that I think this was the Academy of Science required to have a sort of a catalog of the properties, but it was a very small amount. Yes, they were very stressed financially. So at the point when Pierre's father moved in with them, then things smoothed out, and so Marie and Pierre began to talk about what she could do towards getting her PhD. And at that point in time, the big thing was, of course, the X-rays, and working with X-rays and the discoveries that based on Röntgen. But Pierre suggested that she might want to look into Becquerel rays, or uranic rays, whichever name you wanted to use, because there was so little interest in them. It looked like this might be an area where we won't have to compete with others.
Yeah, low-hanging fruit, possibly.
Possibly, right. Now, what's interesting is Pierre knew this because Becquerel had tried to use one of Pierre's instruments to measure the radioactivity. However, he was unsuccessful and kind of pushed it aside like everybody else. And so there's very little interest in the uranic rays at this time. Now, Marie was a very pragmatic scientist. In other words, she wanted to do things in a very structured manner. As a result, she began to study the minerals and look for radioactivity of the minerals. but she was not satisfied with simply using photographic plates because that only gave her information about the intensity, but not really a way of comparing one mineral to another. So Pierre then used his ideas and developed an instrument that allowed her to measure the intensity of the radiation, which combined his piezoelectric effect, an electrometer, as well as a place where the radioactive material was placed in what we would call a ion chamber, positive and a negative plates, and a small voltage would be generated, and this small voltage could only be measured by one of Pierre's very sensitive electrometers, and required you to look at the mirror of the electrometer and then to balance out the charge on the electrometer by adding or subtracting small weights from a piezoelectric crystal. And all this had to be done while you're looking through a microscope at the mirror to see where the line was to come to a 0 point. And Marie was one of the very few people that could do that.
Yeah, to be that dexterous, and especially at that time, to be so delicate. Because how much weight are we talking about moving on and off?
Less than, we're probably looking at milligrams.
Milligram quantities, yeah. So really small amounts.
Very small.
Yeah, and it's still hard to weigh out a milligram even today with the balances we have and things like that.
And the other aspect there is she had to be looking at it for a long period of time. So she would spend hours looking through the microscope window. Now, one of the things that came out of this is that Marie was the first one to have a quantitative way of measuring radioactivity. They also coined the term radioactivity, and they used metallic uranium as their standard, and then compared other materials to that. One of the things Marie found first off, was that thorium was radioactive. And then she began to study all sorts of other minerals and found some minerals, one particularly was pitchblende, which is a ore that contains uranium. And they found that the pitchblende had a much higher intensity than the percent of uranium in the system. And they also found this with a chalcolite mineral, which is copper, uranium, phosphate. And Marie knew the composition of chalcolite. And so she made it. And interestingly enough, when she made the synthetic chalcolite, it had a radioactivity corresponding to simply the amount of uranium in the crystal, whereas non-synthetic chalcolite had almost twice the amount of activity than the amount of uranium. And so this suggested that these minerals, pitchblende, chalcolite, and others, may have contained an element, they thought, more active than uranium itself. And this was one of the first papers that Marie and Pierre produced.
Wow. So that's an extremely systematic way of trying to figure that out. So that was just her personality, right?
Yes. Now, what they did find, and this basically is chemistry, is they took pitchblende, because that was the one that had the highest activity, and began to treat it as what we would call a qual scheme, where we used precipitation of different elements under different conditions. And so she found that in the sulfur precipitates, they could isolate a compound in the bismuth stream. So it had this activity, which they didn't know what it was, but they could isolate it away from uranium, away from most other known elements, except for bismuth. And it had an activity about 400 times that of uranium. But as they went through, they considered it to be a new element, but they couldn't prove it because at that point in time, to prove a new element, you had to have a spectral line that did not correspond to any other elements.
And since they couldn't separate it from bismuth, they couldn't get that purified.
Right. And they couldn't find any new line would have been hidden by the bismuth. In fact, they finally realized later on that for X, it was 1/10 of a milligram per ton of pitch blende.
So they had to process 1 ton, metric ton, I'm assuming.
Yeah, metric ton, 1,000 kilograms.
Yeah.
For 1/10 of a milligram of material.
Of this unknown element.
Yeah.
That's trapped with this bismuth.
Now, what Marie did is she felt so confident that it was a new mineral that she went ahead and proposed that it be named polonium for the country Poland, which was very political at that time because Poland didn't exist. It had been divided up between Austria-Hungary, Russia, and Germany. And so Poland didn't exist, but she wanted the name to be polonium.
An ode to Poland, as it may. And that kind of just stretches into just how political naming has really become, even like recently with a lot of other things, and how the thought process that has to go through for a lot of naming schemes and things like that. But so when they were breaking down this 1 ton of pitch blende, what was the physical cost of that? How was that process done? Because at the time they didn't really have a lab, or they had a really small lab.
Well, what they had been given originally, because the head of the school took pity on them, he gave them a glass shed, which at one time had been used for cadavers in medical school, and where they did dissections, and it was glass because that allowed a lot of light in. And but it had become so, I don't know exactly what the term was, but several of the well-known, for example, Rutherford, when he, this would have been 4 or 5 years after they actually used it. When he saw it, he didn't think it was good enough for even pigs.
Wow.
To operate in.
So that rundown.
Yeah, it was pretty. And so the processing of all the pitch blende was done in large metal kettles over an open fire if they needed to heat it, stirring with long metal rods. And we're talking about tons and tons of material eventually were processed that way.
Yeah. And so how long would it take from start to finish? Would it take days?
Well, I'm trying to remember exactly the relationship, but we're talking about a process where once you isolated, and if we talk about radium, for example, because that was the the one that actually they really focused on, because she realized that there was a better chance of separating it than the bismuth from the X, polonium. The radium came down in the barium fraction, and in conjunction with a chemist, Gustav Biumont, he suggested they could use fractional precipitation as a way of concentrating the new material. In fractional precipitation, you make a saturated solution, and then you allow it to cool slowly, and at different temperatures the fractionation occurs. And so you take the fraction that has the most activity and take it and do it again.
Do it again, yeah.
And do it again. And so we're talking about probably tens of thousands of redissolved and fractional crystallization.
Yeah.
Tremendous amount of work.
Yeah, a lot of back-breaking work for sure.
Right. Now, early on in the process, Pierre had been put up for a professorship at the Sorbonne University. Pierre was not one to promote himself. And as a result, and because he had never graduated from a known university, he was self-taught and by tutors and by his father. And so even though he was known to be probably the expert in crystallography and that area, a lesser person got the professorship. And at that point is when Pierre said, well, heck with this, I'll help Marie. And so then his handwriting begins to show up in her notebook. And they pretty much separated the work. Pierre would be working on the physics side. Marie was working on the chemistry.
So he gave up everything after that point. You know, I guess he was fed up with all the bureaucracy and the politics of all the professorships and things like that, and I can understand that.
Yeah, and also it's obvious that they and Becquerel did not get along. Even though Becquerel gave the last two papers that are part of Marie's dissertation, Pierre did not trust him. And in fact, Pierre was nominated for the French Academy of Science. Becquerel, was supposedly nominating him, and in the end, he again did not get elected. A lesser, older person got elected, and after that, Pierre just said, "I'm done.
I'm done with all this
with
horse and pony show."
Yeah.
But
and and he then did things like work to obtain all the pitch blend that Marie needed for her work. And one of the comments that was made, it was probably good that they were in basically a courtyard area, because a laboratory wouldn't have been able to handle the tons of pitch blend that they had to go through in order to get the radium. Now, time-wise, Marie's, from the beginning to the announcement of radium was about a year. So she began work in 1898, and through that year, I think it was in January of 99 that they announced radium. Again, the paper would have been given by Becquerel, And Becquerel actually obtained several grants for Marie, but he would not tell her directly. He would tell Pierre, oh, you can tell your wife that she got this degree.
Becquerel seems like a very, very interesting character because on one hand he's helping them, but on the other hand, it's like what are his motives? Do you think he was maybe jealous that they were able to do what he couldn't?
That certainly seems I mean, even the entire population, the comments are that her papers, her announcements were not met with, oh, wow, this is great. It was met with, well, who is this? And she's a woman, and well, wasn't she a governess? And how can someone from Poland, be, and she's married to an industrial laboratory teacher? All those things.
So a lot of things they had to kind of fight against to get their name out there.
Yeah, but two of the most significant aspects of her work initially was that they could use the radioactivity to indicate that there were new elements present, and that this was an atomic property as opposed to a physical property, because she was able to show that whether it was a liquid or a solid, the characteristic radioactivity didn't change. So, but interestingly enough, the idea of the source of this radioactivity and the mechanism, Becquerel was still pushing the phosphorescent type activity, that it came from some outside source that came and then caused this activity. Marie actually began to think that it was from the atom itself, and that we may be looking at the destruction of the atom. But even Pierre said, oh, that's ridiculous, because so many people were into the idea at that point in time. Remember, you had Dalton's law, which said an atom was the smallest indivisible portion of an element. Mm-hmm. And so you couldn't think of it
becoming any smaller.
Or flying apart.
Mm-hmm. So what was their understanding of the atom at that time? Like, what was their model they were going with?
At that time, it was the Thomson model of what they call a raisin pudding, type model, because we don't have the Rutherford's gold foil experiment yet.
Yeah.
But Marie became very driven, because after her announcement, she found out, oh, I lost thorium because a German had announced it about 3 weeks earlier. And of course, she wouldn't have known that because of it took a while for things to
travel.
Yeah. Now, what is really interesting is there are 3 notebooks that still exist of Marie's work, Marie and Pierre's work, that led up to the Nobel Prize. One also has to note that those were, when pulled out about 20 years ago, still very radioactive.
Radiation safety wasn't born yet.
Yeah, no, it wasn't. And as Marie began to get things more and more concentrated, she was able to concentrate the polonium to about 400 times the radioactivity of uranium metal. But with radium, she was able to get it to 10 times 10 to the 6th more intense than uranium metal. And so she was able to finally isolate 1/10 of a gram of radium chloride and determine its molecular weight, and also got a spectrum. So this was the end of about a 3-year process.
Mm-hmm.
Yeah. Okay, and so then in 1903, Becquerel, Pierre Marie Curie won the Nobel Prize in Physics for the discovery of radioactivity. Now, at that point, Marie and Pierre were unable to travel to Sweden to give the address, and so Becquerel was able to give the address. During the address, no mention of Marie was made.
Wow. Really?
Best I can tell.
Man,
He talked some about Pierre, but he was not very
keen on talking about Marie.
No, he talked about himself.
Yeah. He seems like a very opportunistic.
Yeah. Well,
good thing our episode on him was so short, you know.
And it wasn't until 1905 that Pierre gave his portion of the Nobel lecture, in which he almost totally put everything to Marie.
Yeah.
So one can say that was a good thing. Now, a couple of other comments that are quite interesting. Somebody came to Pierre and said, "Oh, the French government wants to give you an award." I forget exactly what it was, but it was some high honor. And Pierre just said, "I'd rather have a new lab."
Yeah, I bet.
I don't want I don't want that. I'd rather have a lab. Both of them were, at this point in time, Marie was having a very difficult pregnancy with her second, Eve, and Pierre was suffering from arthritis. His hands especially seemed to get this. Now, there are many stories of Pierre keeping a vial of radium in his watch pocket. And in fact, there's a note in one of the notebooks where he mentioned the fact that he had a rash right where his watch pocket was. Then in the spring of 1906 is when tragedy struck. Pierre was on his way to a publisher to get a book, look at preprints for a book. It was raining, slippery. He fell in a crowded street and was run over by a wagon, and the wagon wheel evidently went right over his head, and that was it. That was it.
Just a few years after winning the Nobel.
Yeah, and that caused Marie to go into severe depression, and that was took a number of years for her to recover from that.
Mm-hmm. Did she still work while she was? Did she pour herself into her work after that point?
For a year or so, she did not work. But she was then appointed to the professorship that had been given to Pierre after they won the Nobel Prize at the Sorbonne. And she began to then start work again. But after his death, there was a period of severe depression, as you might expect.
Yeah. And
she did not do very much.
Yeah, that's so sad.
Now, the one thing that they did is they refused to patent the process for extracting radium from uranium ores. They said that should be something that the world owns. They also would take small amounts of their very expensive concentrates and freely send it to other scientists who asked.
So they didn't care. They wanted to share it.
Well, they wanted to share it, but they were very into getting their Marie was very into getting awarded what was theirs.
Yeah.
But they were also very willing to share with others. Now, the last story I think is appropriate here is with polonium. There was a German who actually finally isolated enough of it to get a spectrum, so to get the spectral line, which was sort of that's what you needed.
The standard.
And so he technically was the discoverer. However, he went ahead and allowed the element to be named polonium, so he allowed Marie to have that.
The naming of it.
Mm-hmm.
Wow. Great guy. That's a good guy. Like, especially thinking about, have we heard about Becquerel and some of these other characters? Mm-hmm. I guess it was it's kind of nice to hear that there were still some nice people within the field.
Yes. Well, there were, and Marie went on to have a somewhat productive life, but it was filled with she was nominated for the French Academy, but was turned down, and so she basically said, I don't want to even bother with them anymore. Mm-hmm. She went through periods of very financial distress, and of course at that point she won the second Nobel Prize in chemistry for the determination of atomic weight of radium. And her atomic weight was almost spot on to what it is today, which is amazing. Mm-hmm. So what we probably need to talk about as we talk about things is the next character that I've been reading about and I really like is Rutherford. Mm-hmm. Was a New Zealander. He was a Kiwi who showed up, got a scholarship to England, and when he got the letter, he was standing on the farm, the front porch of the farm, and he got the letter and told his dad that he'd no longer be picking up potatoes out of the field.
And moved to England.
And he bought passage to England and showed up at Cambridge.
Wow.
So we'll talk about his contributions to this area.
Absolutely. One last thing, though. So this was really the birth of what we consider radiochemistry, the quantification of radioactivity, and this is where it all started. Yeah. So I don't know. I just wanted to make that point, I guess. But yeah, so that's kind of, it's really cool to see like where this form of chemistry that we've both dedicated our lives to really started out from, and the humble beginnings of it, and the work that they really had to go through, and the hardships.
Well, and the time frame here is we started in 1897, mm-hmm. and up to Marie and Pierre and Becquerel getting Nobel Prize in 2003. 2002 was Röntgen's Nobel Prize, and just a short period of time that things have happened.
Yeah.
And we'll see how quickly things, even now, take so long. Mm-hmm. But and also the other aspect that I think we'll see is that science moves from individual workers to collaboration in larger groups as you go through the years.
Yeah. And so the discovery of radium and this Nobel Prize, they won the Nobel Prize for radium. I guess we're kind of seeing it now with AI and things like that, where we're kind of making these discoveries, but we're not really looking into the future of what kind of harm or what are the after effects of certain discoveries, right? Can you speak a little bit about that?
Well, with radium, they began to see that it was a way to treat cancers. But then you also have putting of, for example, there was a toothpaste that had thorium in it because it was going to whiten your teeth. And you had reinvigorators. These were crocks that some had radium in them. Most had just uranium mineral in a stone in the bottom, and you put water in it, and it sort of invigorates the water. There are all sorts of aspects that people, and sadly, because they didn't realize the effects, the radium doll painters are a good example where they were using radium to eliminate the hands of a clock. And they would point their brush so they could paint the numbers on their tongue. And these poor ladies really suffered as a result.
Yeah. So, and I think, and that's kind of what we do as a society with X-rays. We implemented it in a positive way, but we weren't thinking about maybe the possible negatives, and people were getting hurt and things like that. And as with radioactivity, radioactive elements, like you said, they would put it kind of in their water and things like that. There were positives. You could treat cancers with it, but there was also, maybe we took it a step too far, right? And I think that's always something we kind of do with new discoveries. Maybe a little bit safer now, but I think we're kind of getting into a realm.
Well, and I'd have to say that radioactivity tends to be the poster child of something like this. But you have to look at DDT. That was that was developed to cure malaria or to kill the mosquitoes that carry malaria. Or, there are other drugs that have come out which one thought were going to be a godsend, and in turn they had negative results that you really wouldn't want.
Yeah, and it's sad that radiation and radioactivity is the poster child for, I guess, taking science a little too far too quickly. But there's, like you said, so many other examples of supposed to be these godsends, these wonder drugs, things like that, which really turn out to be, more negative than positive. Mm-hmm. And I'm sure we'll get into, I guess the current mindset of what radioactivity is in the world, and maybe how we can move that forward, possibly.
Well, there are some positive aspects coming out.
Especially now, and we'll definitely.
Certainly, it is a way of being carbon neutral eventually.
Yeah.
And my aspect is, I know everybody's getting excited about electric cars, but we have to have the electricity, and whether it's produced by gas or oil or
coal, solar, wind, what's really feasible right at this moment, and and we'll get into that. But all right, well, thank you for listening, and next time we'll talk about Rutherford and his contributions.
Yes.